Hey AP Stats, we are going to talk some more about binomial distributions today. And where we left off was right where we were starting to talk about the mean and standard deviation. So the mean and standard deviation of binomial random variables, where n is the total number of observations and p is the probability of success. So the mean is just n times p. The standard deviation is the square root of np1 minus p. So you need to know these for the Chapter 8 test, but these formulas are formulas that are on the formula sheet for the AP exam. So for your semester final, you'll have those formulas to use. Okay. All right, so we're going to jump back up to, we're going to go to example 7, but it says return to example 6 where 60% of the computers sold have a flat panel display. And you look at the type of monitor purchased by the next 12 people, find the mean and standard deviation. So here let's just label some things. This is our P is 0.6, N is 12. Okay, so our mean is N times P, which is 12 times 0.6. Okay, so if you don't already have your calculator out, grab it. If you multiply those together, you're going to get 7.2. Okay, so on average, 7.2 people get a flat panel display. Okay, the standard deviation we're going to have is the square root of n times p1 minus p. Okay, so that's 12. P is 0.6, so then 1 minus p would be 0.4. For some reason, this part is something that students make a lot of mistakes on. I'm not really sure exactly why. A lot of people try to take shortcuts and use their answer from the mean. I would just definitely, recommend not doing that. Just write out the formula and go ahead and calculate that. Okay, so when you calculate that, you should get 1.697. Okay, so there's your mean, standard deviation. That's it. Okay, you just really got to know those formulas. We're going to skip example 8 for right now because it's a little bit hard to do without me showing you what to do on the calculator. Okay. Okay, so something that happens is the normal approximation to a binomial distribution. As our n gets really large, then it starts to follow a normal distribution. Okay, so the formula for binomial probabilities becomes awkward when the number of trials of n increase. So as the number of trials n gets larger, the binomial distribution gets close to a normal approximation. And so when n is large, we can use normal probability calculations to approximate, hard to calculate binomial probabilities. Okay, so it would follow a normal distribution with n times p as our mean of a binomial. N times p1 minus p square root is the formula for the standard deviation of a binomial. We are going to talk a lot more about conditions, about when we can do stuff like this next semester. But basically this is saying when n is large enough. This is what you would have to check to know that n is large enough to do this. Okay, so as long as the n is large enough, then this would hold true for any type of problem. Okay, so example 9. Our attitudes towards shopping changing. Sample surveys show that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults, if they agreed or disagreed that I like buying new clothes, but shopping is often frustrating and time-consuming. The population the poll wants to draw conclusions about is all U.S. residents age 18 and over. Suppose that in fact 60% of all U.S. residents say they agree if they were asked the same question. Okay, so we have a random sample of 2,500 adults. Okay, so our n is very large. Let's keep track of some things. N is 2,500. Okay, and then what's our p? That's the only other number we were given. 60% would agree. Okay. So find the probability that 15, 20, or more of the sample agree. So we want probability x is greater than or equal to 1520. So we can use the binomial, they either agree or they disagree. So if it's a binomial situation, our probability stays the same. We have each person would be independent and our n we know. Okay? So if I want to do greater than, what do I have to do to get binomial to do this? Well, first of all, are we using binomial PDF or CDF? Yeah, we have to use CDF, okay? And to get it to do greater than, we have to actually do 1 minus less than. So if I'm just gonna write this over here on the side. We just think about like a number line, 1519, 1520, 1521, and it's gonna go on that way and on down to 0. So we want our answer to be 1520 or more. So what do I need to subtract off? I need to subtract off 0 to 1519. So I'm going to do 1 minus the probability x is less than or equal to 1519. And that will tell me the answer. Okay, so to do that, this would be 1 minus binomial CDF. Oops. My n is 2500, p is 0.6, and I'm going to put 1519 in there. Okay, so grab your calculator, make sure you pick CDF, binomial CDF, 2500, 0.6, 1519. Okay, when you get that out, you should get 0.213. So that's an exact calculation. We are also going to go ahead and do a normal approximation and see how close it is. Because the binomial CDF, you can do this. It just gets kind of awkward when you're talking about really big numbers like this, when n's really large. But this binomial, this is an exact answer. Okay, so this is exactly right. So B, we're going to find the mean and standard deviation. So again, mean, n times p. So 2500 times 0.6. So that's 1500. Okay, the standard deviation, we take the square root of 2500 times 0.6, and then 1 minus p, so 0.4. Okay, grab your calculator, calculate that away. Don't forget to take the square root. Oops. So you should get 24.49. Excuse me. Okay, so since n is sufficiently large here, n is 2500, let's go ahead and use a normal calculation to find this value. So since n is large, it's going to follow a normal distribution. Our mean is what we just found in part B. Where is it centered at? 1500. We want to know the probability of 1520 or more. Okay, so 1520 or more. All right, so 1520 minus 1500. Okay, because that's what our mean we just found up here in part B. Divide by our standard deviation. 24.49. Okay, so go ahead and find that z-score. So you should get 0.817. And then we're going to do normal CDF from 0.817 to positive infinity. Okay. So when you calculate that, what do we get? You should get 0.21. Okay, and what we wanted to compare that to was our exact answer from the binomial. Okay, so again, the binomial here is exact, 0.213. Our approximation using normal situations, 0.21. So they're very, very similar. So again, long as n is large enough, this would get you a close enough answer that you would pick the correct one, like on the AP exam, even if it was multiple choice. There's going to be multiple ways to solve things. So long as you check your conditions and know that you can do it, you would get the same answer. So we're going to start to see, this is kind of like the chapter where we're bridging probability situations, and as we kind of move forward into random variables and finding probabilities, we're going to try to use normal stuff as often as possible. So just wanted to show you how they relate. Okay, next question. You have a problem just like this on your test. Okay, on your chapter 8 test, well, chapter 7, 8 test. This is one of your free response questions. Okay, so just note that like this is like exactly like one of them. Okay, Cristiano Ronaldo is a well-known soccer player that plays for Real Madrid. During the 2011 soccer season, of his shots on goal, he scored 45% of the time. Consider his next 3 shots. Okay, and let x equal the number of shots made. Okay. So, he's going to shoot 3 times. So we can write out the sample space for the situations where he gets a goal versus he doesn't get a goal. So I'm going to label these as G is goal and N is no goal. Okay. So we write out the sample space. Okay. I'm going to use like a curly bracket to write out. This is basically just like when you toss a coin when we wrote out like heads and tails, you know, for tossing a coin 3 times. This is exactly what we're doing right now in the same sample space. So we'll start with no goal. So he could, on 3 shots, he could score no goal, no goal, no goal. Doesn't make one. So it's 0 goals made. He could make one of the shots, okay, of the 3, and then it can happen in any order. So he could get a goal the first time and then no goals, or the second time, or the third time. Okay, so that's all the situations where he could get 1 goal. He could get 2 goals in any order. Okay, or he could make all 3. Okay, so this is writing out the sample space. Okay, so we said X is the number of shots made. What are my situations here? On the first situation, how many shots were made? If he was no goal, no goal, no goal. Yeah, 0. Okay. And then he could make 1 goal, or he could make 2 goals, or he could make 3 goals. Okay, so now to find these probabilities. How do I do this easily? Okay, what type of problem is this? Okay, well, what chapter are we in? Binomial. Is this a binomial situation? Yes, we're going to say that his shooting percentage stays the same. Each shot is independent of the others. We know how many, there are 3, and it's either he makes a goal or not. So we have the situation where no goal, yes goal. Okay, 2 outcomes. So for the first one, probability x equals 0. This is a binomial. So binomial, and we're doing 1 probability. So PDF, there's 3 shots. 0.45 is the probability, and then this is just what's going to change. So we're going to do 0. Okay, so it's a binomial. What's the probability he makes 0 shots? So go ahead and grab your calculator, get that in there. 3.45 and 0 for make sure you've got PDF here. Okay, so you should have 0.166. So now when I go and do it for probability x equals 1, the only thing that changes is the 1. I'm going to do binomial PDF again, but instead of the 0, I'm just going to stick in a 1 right there. So it's the same thing, binomial PDF. So just hit second enter and go back and change the 0 to a 1. Okay, so that should be 0.408. and then go back and now change this to a 2, and then change it to a 3 to get the other two probabilities. So go ahead and fill in your table. Okay, so you should get 0.334 and 0.091. Okay, so that's a point. I don't know. What should your probability sum to? Yeah, the table, it's a complete table, so it should sum to 1. Please make sure you have a mental check and make sure your probability sum to 1. I can't tell you how many people make up like so many wonky probabilities in this problem on your test. So yeah, note to self, they should sum to 1. Okay. Okay, so now we can either solve the following questions in a couple different ways. And this is how it starts to happen as we kind of learn more material and see how things are related. Probability he scores at least 2 of his shots. Probability x is greater than or equal to 2. Well, now that we have this table, we can just look in the table and find it. But how did I find these numbers? This is a binomial problem, so I could have done, if I didn't have to make the table, it would have been binomial PDF, 3.45 and 2, plus binomial PDF, 3.45 and 3. Okay, so in this problem we have the table, so I don't have to write out all this binomial probability stuff. But in some problems, you don't necessarily have to do the table, and it goes back to binomial problem. If we have the table, it's just like a discrete random variable, like we talked about in chapter 7. Okay, so there's going to be multiple ways to solve these. When you add those up, you should get 0.425. Okay, B, probability scores at most 2 of his goals. So that's x is less than or equal to 2. So we can add up 0, 1, and 2. You could also do binomial CDF and do from 2 and lower, and it would be the exact same answer. So here we're going to add up 0.166, 0.408, 334. Okay, when you sum those up, you get 0.908. You could have also just done 1 minus the probability of 3, and then that's the rest of the table. So there's lots and lots of different ways to solve these. Okay, what is the mean of x? Now this I really want to show you. There's 2 ways we can solve this. We know this was a binomial problem. So if you remember that formula, it's just n times p. Okay, so our n was 3. Our probability is 0.45. You multiply those together, on average, he scores 1.35 goals. Now, if we were in class, I would just show you this so you didn't have to plug all this into your calculator. But we can also do, since our table problems, how we found the mean of table problems was we took our value, so 0 times the probability, times the value times the probability, down to the last one. Okay? So if you do this in the calculator and just use your list like we did before, you get 1.35. Okay, so the mean's 1.35. You can solve it using binomial, or this was our definition of a random variable. I think it's pretty cool when you start to be able to solve problems in multiple ways and get the same answer. Okay? So you would only have to show one way, but I'm just saying either way you do it, you would still get full credit. All right, we're going to skip this simulating binomial events right now because I want to be able to show you that in person on the calculator to do that. So just go ahead and ignore that right now. Okay, so that is the info on binomial. We are also going to talk about another distribution, which is called a geometric distribution. They're very, very similar to binomial. Okay, there's one change that happens with geometric. So if a random variable x is the number of trials needed to obtain the first success, then the distribution produced by this random variable is called a geometric distribution. Okay, so here are the possible values, the possible outcomes for a geometric random variable are 1, 2, 3, and so on. It's an infinite set. Okay, it goes on forever. And notice that it does not include 0. In our binomial distributions, one of the values was always 0. But here, this geometric does not include 0. Okay, so let's talk about this. So examples of geometric. The whole goal of geometric is you're going until you get your first success, and then you stop. Okay, so you flip a coin until you get a head. Okay, so if you flip a coin until you get a head, what's the first opportunity you had to get a head out of the coin? The first try. So the first outcome is the first try. You can't get 0 because you have to actually flip the coin in order to see if you got a head or not. Okay, so your first outcome, like in your table, is always going to be a 1. That's the possibility of your first success. If it happens on the second try, that means that you didn't get it the first time and you got it the second time. Okay, or on the third try, it means you didn't get it, and then on the third try, you got a head. Okay, so again, the whole goal of geometric is you're going until you get your success. So you roll a die until you get a 3. You attempt a 3-point shot until you make it. So for a geometric setting, the following 4 things must be satisfied. Okay, and so they're very, very similar to binomial. There's only one change. So each observation falls into one of just 2 categories: success or failure. Okay, that's the same as binomial. The observations, we say they're all independent. So each trial is independent of the previous ones. Okay, same as binomial. The probability of success, call it P, is the same for each observation. That happens in binomial. What's the one thing that's going to be different? So go back and look at your notes. These 3 things happen in binomial. What's the other thing in binomial? What's the 4th thing? Go back and flip to I think it's the first page of your notes, binomial setting. There's 4 properties. What's the 4th one? The 4th one is that we know our n. We know how many times, like for example, flipping a coin. I know I'm going to flip a coin 5 times and I'm going to look at the number of heads that occur. The difference with geometric is we don't know that we're flipping the coin 5 times. Here, we're going until we get a head. We're going until we have our first success. So this is the one that's very different. The variable of interest is the number of trials required to obtain the first success. Okay, so if you've got a highlighter, this is the one that's different. Okay, you're going until you have a success. Okay, consider rolling a single die. The event of interest is rolling a 3. The random variable is defined as x is the number of trials occurred until a 3 occurs. Okay, so let's verify this is a geometric setting. Okay, so we're just going to go through those 4 things. Does everything fall into just 2 categories? Yeah, it's either a 3 or it's not. So that's our success-failure situation. Every time you roll a dice, would that be independent? That's our second one. Yeah, each roll is independent. Okay, so far so good. Number 3, the probability of success is the same. Is that true? Probability of getting a 3 is the same each time? Yes, the probability equals 1/6 is the same for each roll. Okay, and then number 4, the variable interest is until we get our first success. Is that what we are looking at here? Yep, we roll until a 3 occurs. Okay, if you have different types of problem all mixed together, this is how you know it's geometric, by looking at what you're looking for. Versus in a binomial situation, it'd be almost the same, except it's going to say we're going to, roll a dice 10 times and look at the outcomes. Okay, so here we're going until we have our first success. Yes, this holds up with our geometric situation. Okay, so let's look at what happens. The nice thing is order matters here. So we can kind of write out the order in which the probabilities are occurring. Let's see if you can see the pattern. Okay, so probability x equals 1. Again, we have to actually roll the dice for it to be success. So we start at 1. So the first time, if I roll a 3, the very first time, what's the probability I roll a 3? Yeah, it's just 1/6. Okay. So I'm also going to have us write these as decimals so we can kind of see what happens. Okay, so 0.167. Okay, so if probability x equals 2, so my first success happens on the second roll of the dice. So what must have happened on the first roll? If I have to roll it twice, the first roll I know I didn't get it. There was no 3. So the probability I get no 3 would be 5 out of 6. Then on my second roll, I get the 3 because I only had to roll it 2 times. So that is going to be, what's the probability I roll a 3? 1/6. Okay, so 5 out of 36 is the fraction. So that's why I want to write them as decimals because most people don't know what that is. 0.139. Okay, are we starting to see what's going to happen? If my first success occurs on the third roll, what must have happened? Did I get it the first roll? No. Did I get it the second roll? No. So we've got 5/6, 5/6, and then on the third roll, I do get it. So that probability is 1/6. Okay, so you multiply that out in your calculator. You're going to get 0.116. Okay, let's just do one more. So if it happens on the fourth roll, what must have happened? I didn't get it on 1, 2, or 3, and then on the fourth roll, I get it. So I must have had 3 failures, and then my last one, my fourth one, is a success, 1/6. Okay, so 3 failures, and then the last one, I get the 3. So you multiply that, you're going to get 0.096. Do you see that pattern? You have, like if you're looking at x equals 4, you had 3 failures and then 1 success. So if I was looking at like 7, what's the probability it happens on the 7th try? That means I would have had to have 6 failures and then 1 success on the 7th try. So that is exactly your formula. Okay. So probability x equals n, so whatever that value is. 1 minus p is your probability of failure. And you have n minus 1 failures, and then probability of p, which is your 1 success. Okay. Okay, so if you like looking at old math that you have somehow seen in all of your math careers and how it ties to this, this is the proof of how you get to where we are. I'm never going to ask you, you don't need to know that, but you've seen a geometric series before, or sequence, and then the sum of a geometric series, like I know I taught this in Advanced Algebra 2, so you guys have all seen this at some point. Then you can sum these up, look at this, and see why the sum of a geometric series is 1. But again, this is only for you. This part is only if you're interested in kind of, they're connected. The stuff that you've learned before and what we're doing now is connected, but I'm not going to ask you about it. Okay? What you need to know is this formula here. This is essential. Okay, so let's try this. Suppose that 40% of the students who drive to school carry jumper cables. Your car has a dead battery and you don't have jumper cables, so you decide to stop students who are headed to the parking lot and ask them whether they have a pair of jumper cables or not. Okay, so let x equal the number of students who must be stopped before finding a student with jumper cables. Okay, so find the probability the first student stopped has jumper cables. So your success occurs the first time. So that's probability x equals 1. So what's the probability I get a success? Yep, pretty straightforward, 0.4. Find the probability that 3 or fewer students must be stopped. Okay, so 3 or fewer. What are my situations here? That is probability x equals, I either got on the first try, or, so I'm going to add, I got it on the second try, or I got it on the third try. Okay, so let's write these probabilities out. See if we can find our pattern. So probability x equals 1, 0.4. Okay, if I had to do I had to ask 2 people, that means that the first one must have failed, and then the second one was a success. So the first is a failure, so 0.6, and then the next one was a success, so 0.4. Okay, the situation where I had to ask 3 people means that I had a failure and then a failure, so 2 failures, and then my success. Okay, so the really nice thing about geometric is that the order matters, and so we can write out the like case by case situations here. Okay, so when you calculate that, you get 0.784. Okay, and just on a side note, I want to show you, you do have calculator commands just like binomial. So you can do probability x equals an exact value, so k. It's going to be geometric PDF, just like we did with binomial. But what you stick in there, we don't know the n, so we don't put an n in there. You're just going to put the probability and then k when you want the success to happen. You can also do less than or equal to with a geometric CDF. And again, you would do P and K, but it's going to sum it up from 1, 2, 3, all the way up to wherever your K is. Okay, so they work just like binomial. The calculator commands do. Okay, the mean and standard deviation of a geometric random variable. So here again, formulas that are helpful you need to know for this chapter test. So the mean is 1 over P. The variance is, okay, notice this is variance too. So the standard deviation would equal the square root of this. Okay, so just note that this formula is for variance. Okay, so here's your standard deviation. You just got to take the square root of it. So the problem that we were just doing, find the mean. So on average, how many people are you going to have to talk to when you find your success? Your first success. So it's 1 over P. RP was 0.4. So 1 divided by 0.4 is going to be 2.5. So on average, your first success happens in between 2 and 3. 2 and 3 people you have to ask. Okay, the variance, follow this formula, is 1 minus P, so 1 minus 0.4, and then divide by P squared, so 0.4 squared. Okay, so 1 minus 0.4, we get 0.6 divided by 0.4 squared. Here's your calculator. So you should get 3.75. Okay, and then the standard deviation is the square root of that number. So go ahead and take the square root. And you should get 1.94. Okay, so again, geometric is very, very similar to binomial in how you solve things. It's just that geometric is you're going until your first success occurs. Okay, it's the major difference between that. Okay, so one thing that does come up is the probability it takes more than n trials, so whatever your n is, to have your first success. Okay, so this formula, 1 minus p to the n, this comes up as multiple choice questions. So you really do need to know how to do this. It just comes up. I'm going to test you on it. It's like a very common AP question to know this formula. You also do, to get x is greater than n, the same thing that we've been using is 1 minus the probability x is less than or equal to n. Does that make sense? Just all the things we're doing for binomial and geometric. X is greater than n, you can do 1 minus the probability it's less than or equal to n, which is the same thing as 1 minus geometric CDF of p and n. So this is fine. I don't care if you solve it this way. It's totally fine. But this formula comes up for sure as multiple choice questions, so you don't want to forget this guy. Okay, so keep track of that. Okay, so let's go over this. Roll a die until a 3 is observed. Find the probability it takes more than 6 rolls to observe a 3. So probability x is greater than 6. Okay, so based on our formula, that means I must have had 6 failures, and then my success is going to happen after that. Okay, So what's the probability I have 6 failures? Oops. Sorry, got a little ahead of myself. Okay. So probability, I roll a 3. Probability of success, P, is going to be 1/6. So what's the probability of failure? It's going to be 5/6. Okay, so if I want my success to occur after the 6th try, I must have had 6 failures. So I'm going to have 5/6 to the 6th. Okay, that's based on our formula. That's going to be the same answer as if I did 1 minus geometric CDF P, my probability of success, which is 1/6, and 6. Okay, so go ahead and double check that you get the same answer either way. Just the geometric CDF, don't forget to subtract it from 1. Okay, go ahead and calculate that. Okay, so when you calculate that, that's 0.335. Okay. All right, and then find the probability it takes more than 12 rolls to observe a 3. Okay, so very same thing. If it's going to take more than 12 rolls, I must have had 12 failures. So it's going to be 5/6 to the 12th power, which is the same thing as 1 minus geometric CDF. Probability of success, so 1/6, and I'm having my success happen at the 12th. Okay, so this is 1 minus the probability x is less than or equal to 12. So either do 5/6 to the 12th or calculate it using geometric, but go ahead and do that. Okay, so you should get 0.112. All right, so we covered a lot of material, both for binomial and then also geometric. We're going to stop and not go over this geometric simulations at this time and wait till I'm back in class to do that. So you guys have a worksheet to work on. You also have a cumulative review to work on. You are going to have a quiz on Friday. So the quiz on Friday is going to include both Chapter 7 material, so don't forget that because your test includes Chapter 7 and 8. So your quiz will be on Chapter 7 and what we've covered so far in Chapter 8. So not the simulations, but binomial situations and geometric. Okay, so you've got some stuff to study. You have worksheets to work on, and yeah, all right, I'll talk to you guys later.